All right, welcome to the Explainer. Today we're taking a total X-ray look into C programming to uncover a pretty surprising secret hiding right inside your code. If you've ever written software that deals with real-world objects, you already know that keeping your data organized is basically half the battle. But what if I told you that the very tool we use to organize our data might actually be secretly eating up your system's memory? So today we're pulling back the curtain on C structures and diving into the hidden cost of memory padding.
So let's dive right into this. To really understand the secret, we first need to look at the messy reality of programming. Let's say you're writing code for a constrained embedded system, and you need to keep track of a complex machine. How do you actually store a robot in your code? I know it sounds like a totally simple question, but when you actually sit down at your keyboard, things get complicated really fast. A robot isn't just one single number, right? It's a whole collection of different states and physical properties that all have to be tracked at the exact same time.
You quickly realize you need variables for absolutely everything. You're going to need a string array for its name. You need a float for its speed. Maybe an integer for its direction. You definitely need to track the battery percentage and, of course, its X and Y position. If you just define these as standard standalone variables, you very quickly end up with a disjointed mess scattered everywhere throughout your files. Just imagine trying to pass all that information to a single function that updates the robot screen. You'd have a function with 6 or 7 different arguments. It's a total headache to write, it's hard to read, and honestly, it's an absolute nightmare to maintain.
Which brings us to Section 1. Enter the C structure, the elegant solution. To fix this chaotic code organization, the C language gives us a really powerful tool, the C structure, which we usually just call by its keyword, struct. A structure gives us a unified way to group variables of entirely different data types into a single, neat little package. By throwing the typedef keyword in there along with the struct, we can actually define cohesive, reusable custom data types that perfectly mirror reality. You can create a structure for a sensor, a motor, a student, a network pocket, or in our case, a robot. So instead of passing around 6 different variables, you just pass around one single robot. And the process to get there is incredibly straightforward. It's essentially just 3 mechanical steps. Step 1, you look at all those scattered, disjointed variables floating around your code. Step 2, you mathematically lasso them, grouping them all together right inside the curly braces of a struct declaration. And step 3, the compiler yields one beautifully clean, unified structure. You've essentially just created your own custom data type that acts exactly how you need it to. The crucial takeaway here is really comparing this before and after. On one hand, you have the absolute headache of tracking individual states, like trying to remember if you called it robot_speed or just speed. But on the other hand, you have the total elegance of a single organized structure where you simply type robot.speed and instantly get exactly what you need. It makes your code incredibly readable and logically sound. But, as with pretty much all things in computer science, this convenience definitely begs a deeper question.
Let's move to Section 2. Inside the memory layout, the X-ray view.
So let's transition from that clean, human-readable code syntax to what the computer is actually doing behind the scenes. We really have to ask ourselves, is grouping these variables completely free? When we tell the compiler to bundle a 1-byte character, a 4-byte integer, and a floating point number all into one single package, does the computer just perfectly stack them together like bricks, or is there a ghost in the machine?
That leads us directly into Section 3, the hidden cost, memory padding.
Memory padding is essentially empty space that the compiler secretly forces right into your layout. Think of it kind of like packing peanuts in a shipping box. You see, a computer's processor really doesn't like reading data from just any random memory address. It heavily prefers reading data in chunks, usually 4 or 8 bytes at a time, starting at very specific boundaries. So to make the processor happy and keep things running fast, the compiler will secretly inject completely empty, wasted bytes right between your structure's variables, just to ensure that the next variable falls on a perfectly aligned memory boundary.
When you look at the actual memory layout here, you can literally see your real robot data sitting right next to empty inserted padding bytes. Say your robot's name is a single character sitting at memory address 0x00. It takes up exactly 1 byte. But your speed is a 4-byte integer. The processor absolutely does not want to read a 4-byte integer starting at address 0x01. It wants it starting at a clean multiple of 4, like 0x04. So what does the compiler do? It stuffs addresses 0x01, 0x02, and 0x03 with completely useless, wasted padding bytes, just to push that speed variable down to the 0x04 boundary. You never asked for those bytes, but they're there anyway, just eating up your RAM.
When we visualize a structure's total footprint, we can easily see the exact cost of this. Depending on how you actually order the variables in your structure, a shockingly significant slice of your memory is just eaten up by this wasted padding. The total size of your structure ends up being much larger than the sum of its actual variables. You might think you're using 5 bytes, but the system is actually allocating 8.
Which brings us to Section 4. Why this matters. Real-world embedded applications.
Now, look, if you're programming a desktop application with 16 gigabytes of RAM, losing a few bytes here and there probably isn't going to keep you up at night. But in highly constrained embedded systems, this invisible cost heavily impacts crucial applications. Just think about network communications for a second. A standard CAN frame in a car only allows 8 bytes of data payload, period. If your structure represents a CAN frame and the compiler injects 3 bytes of padding into it, you are literally transmitting dead space over a critical automotive network. The exact same thing goes for UART packets, streaming sensor data, transmitting GPS coordinates, or sending Bluetooth data to a smartphone. When your bandwidth and memory are strictly capped by the hardware, every single byte counts. You literally cannot afford to transmit ghosts.
Because of this padding, correctly managing your structure declarations is absolutely vital to optimizing your system resources. The good news is, you can actually minimize this wasted space by simply changing the order of the variables in your struct, usually by declaring them from the largest data type down to the smallest. This minimizes the gaps that the compiler feels the need to fill. And understanding this behavior becomes even more critical when you start dealing with nested structures or massive arrays of structures. Think about it. If a single structure has 4 bytes of wasted padding, and you create an array of 1,000 of those structures, you've just wasted 4,000 bytes of precious microcontroller RAM for absolutely no reason at all.
At the end of the day, C structures are an incredibly powerful tool for writing clean, organized, and elegant code. But as we've seen, that elegance comes with a secret mechanic running right beneath the surface. So now that you know the hidden cost of memory padding, I want you to think about your own projects. Look closely at how you're declaring your variables. How much of your code's memory is actually doing real productive work, and how much is just a ghost in the machine?